In this video, we will solve a number of problems related to weak acid and pH. So, at first, let's go again to look at an expression that tells us about a weak acid. So when we talk about a weak acid, we have a generic equation where we say we have an acid, HA, which is in aqueous solution, plus water, which is a liquid. Because it's a weak acid, it has double arrows. So this will produce a hydronium ion, which is in aqueous solution, and it will produce a base, or we call it a conjugate base, which is also in aqueous solution. This acid, as it dissolves in water, it will have an acid constant that we call Ka. Ka of this acid will be given by the product of the products divided by the acid. Remember that water is not involved in this reaction because water is a liquid. So water, being a liquid, is not included in the equilibrium expression. So we need to take note of that. Now, if you want to obtain the concentration of the acid, what you want to do, or if you want to obtain the concentration of a hydronium ion, what you are looking for is this part, the H3O+. That is the one that is going to give you the concentration of the hydronium ion and therefore the pH of this solution. Now, how do we solve problems using the equation like this one here given and the expression given above? Let's look at an example of a weak acid. So here we have a solution of a weak acid, hydrocyanic acid, HCN, and this solution is 0.100 molar. Our job is to find the concentration of the hydronium ion and the pH of this acid. How do we go about this problem? The first thing you need to do is to write an equation for this reaction. So you want to write an equation that is similar to HA aqueous plus H2O liquid to give us H3O plus aqueous plus A minus. So for this equation, our HA is H, it stands for this, and the A in this case is Cn. So HCN aqueous plus H2O liquid in equilibrium H3O plus aqueous plus our A in this case is Cn minus, which is also aqueous. So once you write this equation, we know that the Ka of this equation will be given by H3O plus Cn minus divided by the concentration of HCN. That's what we are going to get as the Ka of this equation. So what I am going to do, I'm gonna write the equation again. So we have HCN aqueous plus H2O liquid in equilibrium with H3O plus aqueous plus Cn minus aqueous. And this equation has a Ka of 4.9 times 10 to the power 10. So that is the acid constant of this reaction. Now the second part, what you want to do is to obtain what the concentration of H3O plus is, because that's where you are going to calculate your pH. As with previous equilibrium reactions, here we also develop an ICE table. So the table will cover HCN, H3O plus, and Cn minus. So I'll have a table that has 4 sections. So 1, let me make them big enough, and at least more straight. So we have 1 here, we have 2 products, so I'll put 2 products here. So our reactant is HCN. We are not putting water because water is not involved in the equilibrium expression. Then for our products, we have all these are concentrations, molar concentrations, and then we have Cn minus, also molar concentrations. So the initial, we have initial concentration here. We know that the HCN was 0.100 molar. At that point, we didn't have any hydronium ion, and we also didn't have any Cn minus. So what is our change? The change, the HCN is losing its concentration to form the hydronium ion. So this one will change by a minus X, while this one changes by plus X, and this one also changes by plus X. So the equilibrium concentration here will be 0.100 minus X. Here it will just be X. Here it will be X. So if we again write the equilibrium expression for this reaction here, we will say that Ka is equal to the concentration of the hydronium ion times the concentration of the cyanide ion Cn minus divided by the concentration of HCN. Now we replace these ones with what we have as our equilibrium concentrations. So up here we are going to have X times X. So we have, for this one the concentration is X, for this one the concentration is X. Down here the concentration of this one is 0.100 minus X. So that will give us our Ka. So if I can continue this solving this problem here. So we'll say that our Ka, we already know what it is. It is given as 4.9 times 10 to the power negative 10. So we'll say that 4.9 times 10 to the power negative 10 is equal to X squared 0.100 minus X. As you can see here, the concentration, the original concentration of HCN is way much bigger than the Ka given here. So original concentration of, so I'll just write here, original concentration of HCN Cn way much bigger than Ka. So here, because of that, we assume X is small. Therefore, assume X is small. In that case, we can ignore the X in the denominator. So ignore X in the denominator. So like we did previously, this expression will be equal to x squared over 0.100. So what it means is our x squared will be equal to 0.100 times 4.9 times 10 to the power negative 10, which gives us 4.9 times 10 to the power negative 11. The x will be equal to the square root of 4.9 times 10 to the power negative 11, which gives us 7.0 times 10 to the power negative 6 molar. This one is the concentration of H3 plus. So now we have the concentration of hydronium ion. We need to test if our assumption is correct before we continue. In this case, we are using the 5% rule. So the 5% rule will tell us that if X is greater than 5%, our assumption is incorrect. If X is less than 5%, our assumption is correct. So in this case, our X is 7.0 times 10 to the negative 6 molar. This divided by the original concentration, which is 0.100 molar, times 100%, which gives us 0.007%. And we know that this one is much less than 5%. That tells us that our assumption was correct. So remember that we assumed that X is small, and based on 5% rule, our assumption was correct, and therefore the approximation is valid. Again, we are saying the concentration of the hydronium ion is equal to 7.0 times 10 to the power 6 molar. Now, how do we obtain the pH? In this case, once you find your X, once you find the concentration of the hydronium ion, then you can go on and say pH is equal to negative log the concentration of the hydronium ion. In this case, it will be negative log 7.0 times 10 to the power 6, which gives us a pH of 5.15. So I will say that the pH of a 0.100 molar solution of HCN is equal to 5.15. So that's how we solve a problem like this one. Let us look at another example. So this is an example where you are given a weak base. So here we have a weak base. We already know how to solve a problem when you are given a strong base or a strong acid. But in this case, you are given a weak base. How do you determine the pH of the solution? The equation is similar. You have a weak base plus water to give you a conjugate acid and OH negative. How do you differentiate between a base equation and an acid equation? A weak acid is going to have hydronium ion as a product. A weak base is going to have OH negative, the hydroxide ion, as a product. So in this equation, we know that this one is a weak base because it has this hydroxide ion as one of its product. So if you want to solve a problem based on a weak base, definitely you are also going to use the KB. So KB will be given as, I'll write this one again, KB will be given as the product, which is NH4 plus OH minus and NH3. As usual, water is ignored. So we ignore water in our expression. So let's look at an example that will give us an idea how we can solve problems when you are given a weak base and then you are also given KB of the reaction. So let us take note of the given KB here. 1.76 times 10 to the power negative 5. So, example, find the concentration of the hydroxide ion and then the pH of a solution that is 0.100 molar ammonia, NH3. And here the Kb to two significant figures is 1.8 times 10 to the power negative 5. How do you deal with a problem like this one? Like previously, you need to start with a chemical equation or a dissolution equation. Here we have our base, which is ammonia. The base will be added to liquid water, and then ammonia will grab a proton from water to make NH4 aqueous, because we know a base is a proton acceptor. And then what remains is a hydroxide ion. And we are given the Kb is 1.8 times 10 to the power negative 5. In a reaction like this one, an equation like this one, to calculate the pH, you first need to determine the OH. Once you know the OH, you can easily calculate the pH. Now, how do we go about it? First, we will say that Kb for this reaction is given as NH4 plus, let me not forget plus here, OH minus divided by NH3. And this one is 1.8 times 10 to the power negative 5. As previously, we need the ice table for this reaction. So I will draw my table. The reactant, there is only one because we don't include the water. So I separate the reactants and products. The products, we have this one and we have this one. So I'll need 2 columns. Yeah, I think I forgot something. I'll need also 2 columns here. Because one column will be for information. So I'll need 2 columns here. And then 2 more columns. In total, 1, 2, 3. In total, I'll need 4 columns. So my reactant is NH3. These are molar concentrations. And then I have NH4 as my product 1. And then OH as my second product. So initial concentration, here we are given 0.100 molar of NH3. But at the beginning we didn't have this, so this will be 0.000. The change As usual, it will be negative X because ammonia is losing to form product. Here plus X plus X. The equilibrium concentration here will be 0.100 minus X, X, and X. So what it means is these concentrations here are going to replace these ones up here. So if I can rewrite this information in the table, I will say the concentration of NH3 is 0.100 minus X. The concentration of NH4 plus is equal to X. The concentration of OH minus is equal to X. But remember, our Kb is given by NH4 plus OH minus and NH3. So if we replace these with these values here, we are going to have X squared minus 0.100 minus X is equal to our Kb, which is 1.8 times 10 to the power negative 5. As usual, assume X is small. So we are going to have X squared over 0.100 is equal to 1.8 times 10 to the power negative 5. Then X is equal to the square root 0.100 times 1.8 times 10 to the power negative 5, which gives us 1.33 times 10 to the power negative 3 molar. We can say that the concentration of OH is equal to 1.33 times 10 to the power negative 3 molar. Now we need to test if our assumption was correct. You need to always test the assumption. So 1.33 times 10 to the power negative 3 divided by the original molarity times 100%. It gives us 1.33%, which is less than 5%. This implies that our approximation is valid. Now, once you know the concentration of the hydroxide, you can go on and say Kw is equal to the concentration of the hydronium ion times the concentration of the hydroxide. This one will be 1.0 times 10 to the power negative 14. Based on that, you can say the concentration of the hydronium ion is equal to 1.0 times 10 to the power negative 14 divided by the concentration of OH minus, which is 1.0 times 10 to the power negative 14 divided by the concentration of OH minus. This one we have found here, 1.33 times 10 to the power negative 3. This tells us that the hydronium ion has a concentration of 7.52 times 10 to the power negative 12 molar. Now, to obtain the pH, pH is always negative log the concentration of the hydronium ion. So in this case is negative log the concentration, which is 752 times 10 to the power negative 12, which gives us 11.24. We can say that pH of 0.100 molar NH3 is 11.24. So let us take note, when we are given Kb to solve the pH problem, we need to find the concentration of OH first. Once we do that, then we can determine the concentration of hydrogen ions or hydronium ions, and then the pH of the solution. So make sure that you watch this video, you complete the video assignment that you are going to have, so that you are ready for problems in class. Thank you.